About a year and a half ago, I had an idea. I wanted to build a robot dog, just like these super cool ones that I'd seen online. There was only one problem. I had no experience and a very tight budget. So, was building a robot like that actually possible? No, but that didn't stop me from building a much simpler version and learning a lot along the way. And in this video, I'll show you the entire development process, from the first CAD model to a robot that can actually walk. And if you want to build one yourself, stick around until the end. Let's begin. Every project begins with an overall concept. A quadruped robot, as the name suggests, has 4 legs, so I started by designing just one leg in CAD. And to do that properly, I needed an accurate model of the servos I plan to use, so I measured them and used those dimensions in the design. And believe it or not, picking the right components for your project is absolutely crucial. I can say that now, because at the time I totally underestimated it and I picked these blue servos, because yeah, they were affordable. However, they turned out not to be the best choice I've made, but more on that later. After finishing the design, I 3D printed the 3 parts of the leg: femur, tibia and hip. The servos fit nicely, so I assembled the whole leg, admired the design's beauty for a moment, and then I moved on to coding. The first code I wrote was the hello world of robotics. I made it wave to me. And after that, I moved on to something a little bit more serious. Inverse kinematics. And okay, I know that in part 2 of YouTube short series, I said that inverse kinematics is super complicated, but it turns out that once you learn trigonometry at school, it feels quite simple, to the point that I can explain that now. Okay, here's the leg, and I want to make the leg tip move to a specific given position, let's say here. To do so, I have to compute the joint angles, so that I know how much each servo has to rotate. Let's name these angles theta 1 and theta 2. First, I compute theta 2. As you can see, the femur and tibia almost make a triangle. I'm gonna draw this side and call it C. Now, as we have a triangle here, we know, thanks to the law of cosines, that the cosine of theta 2 is equal to this. After that, we need to find out the value of C. But here's a right triangle with the sides y and x, so C equals square root of x squared plus y squared. Now we plug that into the equation, use the inverse trigonometry function to get the angle, and we get that theta 2 is equal to this. Now it's time for theta 1. I'm gonna also draw 2 angles, alpha and beta. Alpha is a directed angle stretching from x-axis to the side C, so it's just 8 and 2 y over x. And we get beta, which is an angle between femur and the side C, pretty much the same way we got theta 2, by law of cosines. So beta is equal to this. As you can see, these 2 angles kind of add together to make theta 1. However, keep in mind that alpha is negative, but beta is positive. So in order to sort of add them together to get theta 1, we have to subtract beta from alpha. If the leg was flipped, we would add beta instead. And just like that, we get both theta 1 and theta 2. Wow, now as I look at this, it feels so obvious. However, at the time I was coding it, I didn't really know this, so I got some formulas from the internet, implemented them into the code, so that they work fine, and called it a day. But as I was testing that algorithm, something became clear to me. Although the formulas yielded the right values, the leg tip didn't move exactly to where it should, meaning that the servos had some offsets. First, I remembered that when mounting the servos, I didn't really check whether their arms point at 0 degrees relative to the hip or femur when they are set to 0. Next, I saw that the further from 0 degrees I set the value, the larger the offset. I removed the servos from the leg to test them on their own for a while. I think I spotted the problem. I noticed that these servos don't exactly rotate in full 180 degrees, at least not all of them. I'm not exactly sure now if this is because they were manufactured poorly or due to the issues with generating right PWM signals with the Arduino, but what it means is that Arduino servo.write values don't necessarily correspond to the actual angle the servo had rotated. Knowing these 2 things, the solution was fairly simple. First, I remounted the servos in the right way, then I noted down what value I had to input into the servo right function in order to rotate the servo to 90 degrees, and then recorded these values in the Arduino map function. I repeated these for the second servo and the problem solved. Anyways, having 4 legs is always better than having only one. I mean, that's the main idea of building a robot dog. But without a spine, those legs are pretty much useless. So that was the next part I had to design. The first version was flawed, because the back servos didn't fit. I somehow hadn't thought of that during the design phase. To fix it, I rotated the back mounting, and once the new design was ready, I 3D printed it. This time, the servos and the leg fit perfectly, so I jumped back to CAD, copied the leg, mirroring few parts, and 3D printed everything needed for the remaining 3 legs. With all the parts ready, I assembled everything together, admired the design's beauty for a while, and naively thought of how close to finishing the project I was. It's almost done. Well, no, it wasn't. At least not before it could actually walk. And for that, I needed some key electronics. So I ordered a few things online, and here's what I got. PCA9685, servo controller which receives I2C commands from the Arduino and sends PWM signals, allowing it to control up to 16 servos at a time. Next, power regulator that can reduce voltage to 5 volts needed by servos and other electronics. I also found a battery pack that I had used earlier for a different project. I glued these electronics to the robot's body, connected everything up, and started setting each servo one by one, just like I did before. Well, actually the servo controller used different values. Instead of 0 to 180, it was more like 125 to 500. But again, each servo had slightly different value range, so I just tuned them individually. In the meantime, some of the servos broke, and when I replaced them, I used a slightly different model. From that point on, I started to slowly replace all the remaining blue servos as well. And just like that, all the hardware was done, meaning the only thing left was to make it walk. But how do these robots even do that? There are 3 main ways a quadruped robot can move: walking, trotting, and running. At that point, I was fully aware that my first design wasn't exactly optimal. I knew for sure that there was no way it could trot, let alone run. So I decided to focus on just making it move somehow first and worry about design's improvements later. That meant the only realistic option was to implement walking gait. Walking means that only one leg is lifted at a time, while the other 3 stay on the ground and push the robot forward. Because of that, the robot keeps its balance, and the extra leg on the ground helps prevent it from collapsing due to weak servos. With that in mind, I coded a simple walking sequence, nothing fancy really, and after that, finally field testing, well, indoor field testing, not sure what to call it exactly. Yeah, it clearly needed some changes, so I observed it for a while and spotted 3 main issues. First, the spine. Take a look. When a leg is raised, the spine bends and forms an arch. The robot struggles to stand still even on 3 legs. This part simply couldn't be so flexible. Next, smooth leg tips. When the robot walks, or at least tries, the legs slip, meaning that instead of pushing the robot forward, they basically do nothing, making the walk very inefficient. And at last, once again, the servos. Their lack of power caused the robot to frequently sit down and refuse to move any further. Fortunately, however, the solutions to these problems were pretty straightforward. First, I redesigned the spine to make it much more rigid. Then, I chopped up a Lego tire into small pieces and glued one to the tip of each leg to improve grip. And finally, I replaced the blue servos with a slightly stronger model. Well, not all of them. I left the blue ones at the top. With the improved design, my next goal was to implement a trotting gait. Trotting is more efficient than walking, and is actually how most modern robot dogs move. It works by moving two diagonal legs at the same time, while the other two stay on the ground and push the robot forward. However, before moving on to trotting, I wanted to add one very important feature. Take a look at this leg. It moves from one position to another. Notice anything weird? The leg tip doesn't really follow a straight path. And that's a big problem, especially when the leg is on the ground pushing the robot forward, because if it doesn't move in a straight line, it can easily make the robot tip over and fall. Instead of simply telling it to move from one point to another, we add a few intermediate checkpoints between these 2 points. Basically, we get the differences of the end and the start coordinates, then we divide this by the number of checkpoints, and then we iterate and add these small offsets to the position each time. This way, the leg moves only a tiny bit at a time, ensuring that it follows a straight path at all times. Going back to implementing the trot, here's how it works. Each leg moves between 4 points, A, B, C and D. Two diagonal pairs of legs are offset by two phases, meaning that when one pair is in the air at point B, the other pair is at point D. When the first one moves to C, the other moves to point A, and so on. That's basically the core idea behind a trotting gait. However, in practice, that wasn't enough. I had to spend some time adjusting the positions and tuning a few other things. I eventually figured out that each step needs to be relatively small and the robot's body can't be too high or too low. This configuration makes the robot more stable while trotting. Okay, enough talking. Let's see how the robot performed. So the robot moves, everything's fine, and the project is finished, right? Well, no. What you have seen here and in part 6 of the YouTube short series was only part of the truth. Now, take a look how the robot performed most of the time. Back then, to predict whether it would work for even a while, I could basically flip a coin. That meant, once again, that some things needed improvement. I observed the robot and noticed that the main problem was, yet again, weak servos, even after replacement for stronger ones. At that point, I seriously asked myself why on earth I hadn't chosen the right ones in the first place. As I mentioned earlier, picking the right components is absolutely crucial, and it saves you many problems along the way, for example, like this one. So the servos I chose earlier weren't exactly ideal for this project, but what could I do now? The most obvious option was to buy better servos, but I had already upgraded them once and didn't want to spend even more money. So the servos had to stay. That meant I had to look for other solutions. First, I increased the voltage from 5 volts to around 6 volts. More voltage means more power, and more power means stronger servos. And it helped. The robot didn't fall as often, but it still wasn't enough. If I couldn't make the servos move more weight, why not make them move less weight? So, reducing the robot's weight was the second thing. The spine was the heaviest part of the robot, so I designed it to be shorter and thinner. The hips needed a redesign too, so I simply made them less bulky. These changes reduced the robot's weight exactly as intended. And the third thing I did was shorten the femur. Why? Each servo produces torque, which is force multiplied by length. If torque can't be increased, the only way to increase force is to reduce the length. To be honest, I didn't think about this at all in the first design. I just picked a random length, saw that it looked cool, and left it that way. But now I know, the shorter the leg segments, the stronger the leg becomes. With all these adjustments, the robot finally started trotting nicely and steadily. Take a look. That was the point where I could have ended this project. But then I remembered something. The servos at the very top of the robot weren't actually doing anything useful, which meant only one thing. It was time to implement inverse kinematics in 3 axes. This time we begin by solving the angle of the side servo. Now, the coordinate system changes slightly. The x-axis represents sideways movement, y stays as the up and down axis, and the new z-axis corresponds to forward and backward movement. As you can see, when the side servo rotates, the leg tip changes its x and y coordinates. Let's pause the motion right here. I'll draw a line from the origin to that point and call its length b. From now on, I'll refer to the hip length as L4. You can clearly see that there is an angle between B and L4. Let's call this angle alpha 1. We can also mark another 2 angles. Theta 1, which is the directed angle from the x-axis to L4, and beta 1, which is the directed angle from the x-axis to the length B. Beta 1 is simply a tan 2 y over x. And if we add alpha 1 and beta 1 together, we get theta 1, the angle we'll use to rotate the side servo. So far so good. Now we just need to calculate alpha 1. We know that cosine of alpha 1 is equal to L4 over b, where b is square root of x squared plus y squared. Solving for alpha 1, we get that alpha 1 is equal to this, and putting everything together, our final equation for the side servo angle becomes something like this. And just like that, the first angle is solved. 2 more to go. To solve the remaining angles, we do almost the same thing as before. The difference is that earlier we only used y, but now, since the coordinate system has been rotated by theta 1, we need to work with the combined length a plus L1. Here, L1 is simply the height of the shoulder, and a is defined as square root of b squared minus L4 squared. From here we follow the same approach as we did in 2 axes earlier, and calculate the remaining angles. And just like that, we now have inverse kinematics for the leg in all 3 axes. That means we can finally use the side servos to create new movements. Until then, the robot could only trot forward, so I simply reversed that sequence, and just like that, the robot could trot backwards. The next movements I implemented were sideways trots. They are very similar to forward and backward motion, except each leg moves sideways instead. But the most interesting one is turning. To make the robot turn, front and back legs have to move in opposite directions, like that. And that's it! 5 new movements implemented. At this point the robot was basically finished, but I still wanted to add a little cherry on top, or in this case, on the bottom, an ultrasonic distance sensor. Sometimes the robot loses balance or runs out of power and sits down, but it has no way of knowing that and just keeps on trotting. So I mounted an ultrasonic sensor facing down, which continuously checks the distance to the ground, and if the robot's body is too low, it stops the movement and starts a recovery sequence, which makes the robot stand up again before continuing to trot. It might sound a bit primitive, and MPU 6050 would probably work better here, since it can measure the robot's tilt, but I ran into several problems while trying to implement it. So in this case, the ultrasonic distance sensor was much simpler to use, and it does its job surprisingly well. Sits down, and the recovery sequence brings it back on its feet. And with that, the project finally comes to an end. What started as a simple idea turned into months of learning, testing, and fixing mistakes. If you want to build this robot yourself, you'll find all the files, code, and list of components linked in the description for free. And if you like this project, please consider subscribing so that you'll never miss any future one. Thanks for watching.